Now we're going to look at one of the examples that I would perhaps perceive to be more complicated and that might throw you in an exam because perhaps when you read the question you think that you might be missing some of the key information. However, I'm going to take you through a method that should help clear up some of these problems. So the question says, it takes the 81 bromine ion 2.83 times 10 to the minus 5 seconds. Okay, so I'm going to label that there as my time to travel along a flight tube in a mass spectrometer. How long would it take the 79 bromine ion to travel down the same flight tube under the same conditions? So we've really only been given the time of the ion of interest, the first ion of interest. So we're going to call the 81 bromine ion, we're going to call that ion number 1, and we're going to call the 79 bromine ion number 2. Now let's have a look at the information that we've got. We know that we can work out the mass of bromine 79 by, and remember this is in grams to begin with, so that means we've got 1 mole of these ions to be 79 grams. So we convert that to kilograms by doing 79 divided by 1000, and remember divided by 6.022 times 10 to the 23. Okay, that will give us the mass of 1 ion in kilograms. I'm going to leave that and not actually work it out now because I'm going to plug that directly into the calculator when we get to it, and that will sort of help to improve the accuracy of our answer. And sort of avoid rounding errors. But you do have to be careful and watch out for calculator error. Improve the accuracy of answer by typing into your calculator at the end. But that's how we're going to be working out the mass. We know we've got the time for mass for ion number 1. So we're going to say T1, as we're going to call this M2. And T1 is equal to 2.83 times 10 to the minus 5 seconds. And that's in seconds, so we're happy with that. And again, we can work out the mass of ion number 1 in the same way as here by doing 81 divided by 1000 divided by 6.022 times 10 to the 23. Okay, so now we've got information for the mass of ion 1. We've got the time of ion 1. And we've got the mass of ion 2. Okay, and the question is, what is the time that it takes ion 2, so T2, to travel down the same flight tube? So perhaps you're wondering now, well, what about the distance? And what about the kinetic energy? Does it not matter that we don't have values for these? And in reality, it doesn't matter. So I'm going to return to this equation here, that the time of flight is equal to the distance times the square root of the mass divided by 2 times the kinetic energy. Okay, so for ion, let's call this ion number 1, so T1. Okay, put that in pink there. Is equal to distance times mass 1 times 2 times the kinetic energy. Well, we can say that T2 is equal to distance times mass 2 divided by 2 times the kinetic energy. Now I want you to question to yourself, well, what is it about these equations that is the same? Well, we can see, because we're working in the same flight tube, that means the distance will be the same. Okay. And the kinetic energy that each ion is given is going to be the same, because as the question says, it's given under the same conditions. So essentially, if we manage to get all of our constants and the variables on the same side of the equation, okay, we might be able to do a bit of cancelling. So let's have a look at how we might rearrange this to get all of our variables and constants on the same side. So if T1 is equal to distance times mass of 1, so we know that these two are our constants and mass and time are our variables, we can say that T1 divided by the root of mass 1, okay, because it's timesing over here, so it's going to divide when we bring it to this side of the equation, is equal to the distance divided by the square root of 2ke. So that's for ion number 1. And for ion number 2, we can say that T2, and we're going to rearrange this in the same way, is equal to the square root of M2, divided by the square root of M2 is equal to the distance times the 2 times the kinetic energy. Now, if both these terms, T1 over root M1 and T2 over root M2, are both equal, to distance divided by 2 times square root of 2 times ke, then T1 over root M1 must equal T2 over root M2. Perhaps you'd like to pause the video and just sort of take some of that in, rewind it if you like, okay? But what we've done is bring all the variables on one side of the equation and the constants, okay, because these are the same in both equations or both circumstances. We can say that the time flight divided by the mass of each ion is going to be equal to one another because they both equal whatever that value that would give us there, which is why we can cancel out this from our equation. And then we suddenly realise that we have all of this information, okay? So if we scroll back up to the top, we can see that T1 is equal to 2.83 times 10 to the minus 5, okay? So just pop it down here. But actually, perhaps what we want to do first is actually just rearrange this because what we don't know is T2, okay? But with a simple bit of rearranging here, we can say that T2 is equal to T1 divided by root M1 times, okay, because it's dividing over here, so when we bring it up, it's going to multiply, times the square root of times the square root of M2. So T2 is equal to 2.83 times 10 to the minus 5. And here, as I said, I was going to put everything in the calculator together, so you do have to be a bit careful, so I'm going to put some brackets around here. Divided by 81, because that was the mass of 1 mole in grams, divided by 1,000 to turn it into kilograms, divided by 6.22 times 10 to the 23. Okay, so I might want to put some brackets around there. And I was going to work that out on my calculator and times that by the square root of 79 divided by 1,000 divided by 6.022 times 10 to the 23. Okay. And we put that into the calculator and our answer comes out with 2.76 times 10 to the minus 5 seconds. Okay, T2. Now if we compare that to the value of T1, okay, which is 2.83, okay, so 2.76 times 10 to the minus 5 seconds is 79 BR plus, whereas the comparison 2.83 times 10 to the minus 5 seconds is 81. And if you remember, the lighter ions will reach the detector first. So which is the lighter of the two ions? Well, this is the lighter. So we would expect this to reach the detector first. And that's what our answer shows us. So it's always worth checking, okay, in your answers to see, does my answer make sense? And if it doesn't, go back and check. Remember, showing your workings you go throughout the question will really help you maximise the number of marks. If you make an error, the examiner can clearly pick up on where you've gone wrong and perhaps give you some error carried forward marks. So I invite you to go back through this question now and to see if you could have a go at it without my workings as well. Good luck!